All right, chapter 16, section 1, the structure of the atom. And this is going to be our lecture. Okay. Um, Structure of the atom. First of all, scientific shorthand. Okay. We use scientific shorthand, and our shorthand is simply the symbols on the periodic table. Okay. Symbols on the periodic table. And instead of writing down boron or carbon or nitrogen or oxygen, we're just going to write down the symbol. This is a scientific shorthand. This is an easy way of doing it. Why do we do that? It's simple, because if we have something like this, for example, I'm going to write this down. Dihydrogen monoxide. Okay, dihydrogen monoxide. All this is simply water, H2O. We use scientific shorthand. If I'm writing a paper about dihydrogen monoxide, I'd have to keep writing it over and over and over again every time I wanted to write it down. I would have to write this out. But because of the periodic table and those symbols and the shorthand, scientific shorthand, we don't have to do that. We can just write down H2O instead of dihydrogen monoxide. And it makes things easy, okay? Now, number one here, what are the names, our essential questions? What are the names and symbols of the common elements? Right here they are. Aluminum, the symbol is Al. Calcium, Ca. Carbon, C. And so on down through here, all right? So if we look at the periodic table, you'll notice that each element has a symbol. Boron is B, that's simple. Carbon, C. But as we get farther down in here, when we get to things like silver, if you look at silver, the symbol is Ag. What is Ag? Ag is Latin, okay? And the reason we used Ag is because Si and S are both gone. Se's gone. All right, let's do something to where we can identify silver. We don't need all of these letters in there, so we just use the Latin and makes it easy. The Latin for gold, Au. Mercury, Hg. All right. And when you see that type of thing, it's just because we've run out of letters. You can only have so many combinations there. Some of the other elements are named after famous people like Einsteinium, fermium, lawrencium, nobelium, after the Nobel Prize, the creator of the Nobel Prize. Okay, so they are also named for places that they've been discovered. Americium, Berkelium, Berkeley, California, Californium. Okay, so they name them after people. They name these after places they've been discovered, that type of thing. The only reason that this is down here so it fits on a sheet of notebook paper, okay? That's why these have been pulled out and set down here, but they're part of it just like the others. All right. So we use this scientific shorthand just to make things easier for us when we go to write it down, okay? Now, here's the most common elements and their symbols. You should know those or look at them. I'm not going to make you memorize a periodic table. Don't worry. All right. Now, we have atoms, and atoms are the smartest particle. At least that's what we used to think. Now we have subatomic particles. So we have atoms, and I'm going to write this down. Atoms. And all atoms are divided into a nucleus. All atoms is not divided. All atoms have a nucleus. Okay. And in that nucleus, we have protons. And protons have a positive charge. So protons have a positive charge. And here you can see some protons right here. a positive one charge. And then also in there, we have neutrons. And neutrons have no charge. Okay, a neutron has no charge. So let me put in here neutron. Neutrons, they're neutral. They have no charge. We'll just go like that, no charge. And then cruising around really fast outside of these, of my nucleus that's in the middle right here, this little cloud back here, the electron cloud, has, you got it, electrons in it. And electrons have a negative charge. Okay. And a lot of times, just you're going to see me for electrons, since they're negative, I usually will go like this: an electron with a negative charge. Okay, E means electron. Electron with a negative charge. Now, protons and neutrons are not, we always thought they were the smallest there were electrons, protons, and neutrons, but we found out that there are smaller particles. And we found these out because of the particle accelerator. Particle accelerator, okay, that looks like a cool color. Let's try that. And protons and neutrons are each made up of something called quarks. Okay, like you'd say a quart of milk, a quark. All right, there are 6 unique different quarks, and we find them with the Tevatron or with a Large Hadron Collider. Right here, they get particles like a proton accelerating at very high speeds, and then they smack them into each other. Okay, they smack them into each other, and they end up with these different quarks. They are called top, the bottom, and of course the Tevatron's in the United States, so we give them names that we made up here. So that's top quark, bottom quark. There is the up quark and the down quark, and then my two favorite. There is the strange quark, and there is the erase that, messed up. There is the charmed quark, charmed quark. All right, so top, bottom, up, down, strange, and charmed. Top quark, the search for quarks, the hardest, the 6th quark, the hardest one to find was the top quark. So if you ever, and they do put it on the ACT, they'll put it on different things. They'll be like, what is the hardest quark to find? Top quark. That's all you have to put. It's top quark. Everybody knows what it is. Okay. And what that top quark is, and I have 2 protons here. Let me rearrange it. Let me just erase this and do it again. It'll make more sense, hopefully. Here's my camera. All right. I'm going to draw a camera in here. That's taking a picture of these quarks as they collide, or as a couple of protons collide. Here's my camera, and it's taking a picture in this direction, down this way. And down here, I'll have a proton. And then I get another proton accelerating very fast. Boom, and I smack these together. When they smack together, they bust up into quarks. Okay? And when they bust up into quarks, geez, oh Pete, they'll bust up. Now, the top quark, the reason it's called the top quark and it was so hard to find is because it would shoot straight up into the camera and they didn't get an image of it. All the other ones just busted off, okay, in these directions like this. So it was hard to find that top quark. They finally found it, and everything was wonderful and dandy. And there's a story behind it, but we don't need to know that story. Okay, so scientists and engineers use models, and the model we use is the atomic model we use today is this right here, the electron cloud model. There's all kinds of different models in here, but the electron cloud model is the one we use. This is pretty interesting too. This guy right here, Dalton. Dalton is a school teacher, okay, and he It's in England before there's electricity, before the gases run through the little school he's at. And he comes up with the idea of the atom. Okay. Democritus, way back 2000 BC or something like that, he stated there were atoms, but here we are right here. Democritus proposed the idea of atoms. They're tiny particles that make up all matter. But then a guy named Aristotle said, nah, I don't think so. So nobody even thought about it for another 2,000 years until Dalton came along. And what Dalton did is, it was a dark, rainy day, and Dalton came in to teach. And I'm going to draw. I'm not very good at drawing these things, so just bear with me, okay? Hopefully you've seen something like this before. Okay, it's a scale, and down here there's a plate hanging here. And there's a plate on this side, and this is how we tell if this is an early balance. Okay, you could set an there's a horrible drawing, but you could set objects here. All right, you could put some gold over here, and then some weights over here to find out how much it was worth, and it'll tip like this. The scale will tip one way or the other, depending on which thing's the heaviest. It's a horrible drawing, but I'm trying. All right, it tips one way or the other. Now, what Dalton did is Dalton walked into the classroom and he put a candle on this thing. It was dark out, so he put a candle on this and he lit that baby up. With a little fire in there, huh? He lit this candle up and it was burning. All right. And when he first did that, as he did this, my balance was like this. I'm just going to say, here's the candle. And on this side, nothing. Okay. He didn't have anything at all on this side. And he noticed as the candle burned, the balance started doing one of these. Okay. It was showing a loss of weight or a loss of mass. And as the candle burned, the closer and closer it would get to being level again until the candle would be gone and it was level. It was even on both sides. It was balanced again. So he said there has to be, that has to be going someplace. Remember, conservation of matter. You can't create or destroy matter. So Dalton said this thing's got to be going someplace. He came up with the idea of atoms. He reinvented the idea that Democritus started saying, look, there's got to be atoms. They're out there. We just can't see them. He thought the atom must be what I'm smelling in the candle. The atoms are turning into smoke. They're turning into smell. They're turning into melted wax. All right. So he reinvented the idea of atoms. And here was his model. Just a plain old sphere. J.J. Thomson came along, and J.J. Thomson is the one that discovered there were electrons. Okay, there was a positive, and then there were negatives on the outside. Rutherford, who was J.J. Thomson's student, found out that it wasn't like this. It wasn't like a ball of Play-Doh. They call it the plum pudding model. But it wasn't a ball of, we'll say, cookie dough, chocolate chip cookie dough. It was actually dough with the chocolate chips cruising around. Or it was like the sun with planets orbiting. All right. Rutherford's student, Niels Bohr, went a step farther and said, hey, look, this just is not random. There's actually energy levels that these things travel on, these electrons travel on. That brought us to the modern day electron cloud model of the atom. All right. In this electron cloud model, the electrons move so fast we can't really tell where they are. They're hard to see. The darker blue, the more apt there is to be an electron there. Okay, so in the case of this electron cloud model, the one we use today, the darker blue areas, here's some lighter blue, the darker blue, the electrons are going to be found in the darkest blue. They could be out here, but they move so fast. If they're way out there, they don't stay there very long. Okay. Another pretty neat thing to talk about is and it shows an electron here going out here, when an electron goes backwards, it gives off a photon of light. That's what you see. That's what's going on a lamp, in a light bulb, any of that type of stuff. It's electrons bouncing around energy levels, going from one energy level to the other. Okay? And that is it for this lecture on 16.1. I hope this